At some point, you may be interested in integrating a function from some finite value out to infinity, or back to negative infinity. For example, if you look at the function y equals 1 over x, you may want to try to find the area from x equals 1 all the way out to infinity. We know this has a horizontal asymptote at y equals 0, so this function never crosses this x-axis. It just goes forever. And we may want to get some sort of measure for that area underneath the curve. So we could ask for something like this, the integral from 1 to infinity of 1 over x. It may seem like, because this goes on forever, that this automatically should have infinite area. That's a reasonable thing to say, but it turns out that that's not the case. We can define very precisely how to tell when this will give us an infinite area and when it's finite. Sometimes it's one, sometimes it's the other. For example, in the context of statistics, people have developed certain functions that model specific situations where you can have something like this function, y equals 2 over pi times x squared plus 1. And the way this works is that x can take on values, negative values, positive values, and what you're interested in a context like this is what is the probability that this variable, if I just choose a value at random, that value will land somewhere in between whatever values I'm choosing. So maybe this value and this value. If I want to know the probability that the value will be between here and here, then I can just integrate the function. So the area under the curve gives you the probability as a decimal that your value will be between this number and this number. This is super useful in statistics. What I want to point out just to start out here is that integrating out to infinity has a meaningful value here. So if you understand this setup, that the probability is given by this integral, then the probability that your random value that you choose will land between negative infinity and positive infinity should be 100%. Should always land somewhere in there. So I'm going to integrate that function from negative infinity to positive infinity, and I should get out a value of 1, because 1 as a decimal represents 100%. The first thing that I'm going to do for this, though, is I'm going to say, since this function is symmetric, I can integrate from 0 to infinity and then just double that answer. So this is the same thing as 2 times the integral from 0 to infinity of that function. Another thing that I'm going to do is pull out the constants from the numerator and denominator. So then I'll just have 1 over x squared plus 1. I know the antiderivative of that is arctangent of x. And then the last thing that I need to be able to handle is how to integrate to infinity. So what I'm going to do is I'm going to integrate from my bottom value, which I've chosen to be 0. So I'll start here, and then I'll go out to just a general positive number. I'll call it t. I'll integrate from 0 to t, and then I'll take the limit of that value as t shoots out to infinity. So as you pick larger and larger values of t, you get bigger and bigger numbers, and if that area is finite, you can find the finite area by taking the limit of this area as t shoots out to infinity. So I'll have the limit as t goes to infinity of the integral from 0 to t of this function. Pulling canceling out the 2 over pi, so I'll get 4 over pi. All right, if I integrate this function, I get arctangent of x. So I've got arctangent of x for the antiderivative. I plug in t and 0 into that. That gives me arctangent of t minus arctangent of 0. All right, arctangent of 0 is 0 because tangent of the angle 0 is the ratio 0. So I know this goes to 0. And then I've got to think about what happens to arctangent as the argument t goes to infinity. To think about that, I'm going to think about the fact that tangent shoots up to infinity at pi over 2. So this is the graph of tangent. That makes arctangent shoot out to, well, arctangent instead of going up the y-axis goes up the x-axis because you're switching the x and the y. So arctangent will look like this, and because tangent is going to infinity at pi over 2, same thing happens here at pi over 2. So this limit is pi over 2. And why am I getting 2 here? I think I set up this problem wrong. I wanted to get 1. I expected to get 1 instead of 2. So I must have set this up wrong. I must have remembered incorrectly. I'm guessing that the deal is if you set it up with a 2 on top instead of a 1 on top, then you don't need to integrate out to negative infinity. Yeah, that's right. So I should have set this problem up differently. Well, instead of going back through it, what I'm going to do is say that this should have been a 1. So then this would be 1. And then that would make this a 1. So my setup was slightly off, but what this shows is that if I had taken a constant multiple of the function that I chose here to begin with, then I would have a proper, what they call probability density function, so that when you integrate it from negative infinity to positive infinity, that's saying that the probability that your random variable will take on a value somewhere in there is 1. So 100%, that's what we were looking for.